Congratulations to finishing week 2. We are now starting our last week, week 3. I don't know how the time has gone by so quickly. And what we're going to be doing is we're going to be leaving behind probability, and we're moving to our next topic, which is number theory. And number theory studies numbers in a couple different ways. We look at specifically prime numbers and divisibility. And then we look at some different ways for kind of counting numbers as we continue on this week. We're going to learn something called modular arithmetic, and it's a really interesting topic. It's actually one of my favorite topics. And I didn't actually learn modular arithmetic and number theory until I was in college. And it was actually a 300 level. Just, for context, when you start college level classes, if you take calculus in high school and get credit, you typically start in like the 200 levels, and then you get to the 300 levels, by the end of your first year, maybe your second year or so. So I actually didn't see this stuff until like my second year of college, probably. So I'm really excited for you guys to learn a bit about it. It does come up pretty frequently in competitions, and it's a really interesting and useful skill to have to be more familiar with the numbers that you're working with. So we're first going to kind of touch back to primes and divisibility, and this is stuff that you guys probably saw, way back when in elementary school. So a prime number is a whole number whose only factors are 1 in itself. Numbers which have more than 2 factors are called composite. To find all the prime numbers between 1 and 100, we're going to do an exercise. The sieve of Eratosthenes, not really good at pronouncing those crazy long names, so I'm not going to do him justice. It's an ancient algorithm used to identify prime numbers. We use a sieve to find all the prime numbers that are smaller than 100. So we're going to use the diagram on the next page. We've got all the numbers 1 through 100. And I'm going to kind of color code this. So first step is cross out 1 by shading the box completely. 1 is neither prime or composite. 1 is kind of like the awkward case. And I'll kind of touch back to why 1 isn't used once we get a little bit further in this. I'll come back to that concept. Next one, use a / to cross out all multiples of 2 starting with 4. Keep in mind that 2 is our first prime number, so I'll kind of maybe put a box around 2 to say that we're not going to skip it. Okay, so all the even numbers. So we're just going to keep going. And you probably are recognizing a pattern that the even numbers, you can kind of just go in rows. Oops, sorry about that. So feel free to make the process a little faster if you so desire, rather than going horizontally. Okay, so that's step 2. Use a backward slash, so just slash the other way, to cross out multiples of 3 that are starting with 6. 3 is a prime number, so I'm going to also kind of highlight my other prime number, and we're going to do multiples of 3 starting with 6. So 6, 9, 12, 15. Right, and you'll probably recognize some patterns here too. So I'm just going to pause it and just keep crossing out. Okay, so I finished those out. You also are probably seeing that multiples of 3 have these nice lines that get formed as well, which is kind of cool. Similar to how we saw that the even numbers, we could kind of just go like straight down, oops, yep, straight down. I thought I did the wrong row for a sec. So some of those patterns make it a little bit faster to cross these out. Okay, let's go back and double check. So we've done step 3. Step 4, multiples of 4 have already been crossed out because they are multiples of 2. Check. Draw a square on all multiples of 5, starting with 10. Okay, and maybe I'll kind of shade these then. So we're going to do a square around multiples of 5, starting with 10 because 5 is a prime number. 5 only has 1 and 5. Okay, so I'm going to do a square around multiples of 5. And you'll probably realize that. Like you've got all these guys, right? Anything that ends in a 5 is a multiple of 5. And all your multiples of 10 are also multiples of 5. Whew. Okay, we got those real quick. Okay, next step. Multiples of 6 are already x'd out because they are they have 2 and 3 that go into them, which is kind of nice. So all your multiples of 6 should already be gone. Circle all the multiples of 7, starting with 14, as 7 is prime. 7 only has 1 and 7. So we're circling. So starting with 14, so 21, 28, 7 times 5, 7 times 6, 7 times 7, times 8, times 9, times 10, times 11, and I actually don't know 7 times 12 off the top of my head. Times 12, looks like it's 84. And then 91 is the final one. And 98. There we go. Yeah, my 7s are not quite as easy for me to remember those multiplication facts when I get higher up. It's kind of weird. Some people I think are, you know, really good at those kinds of things. Some people aren't as good. It's kind of funny to think about that. Okay. Multiples of 8 have already been crossed out because they are even. Check. Multiples of 9 were crossed out because every multiple of 9 is also a multiple of 3. And multiples of 10 were done because 2 times 5, right? Anything that's even is also going to be a multiple of 10. Cool. So all the remaining numbers are prime. So let's just highlight all our other ones. Got 11, 13, 17, 19, 23, 29, 31, 37, 38. Oh, I don't know why. That should be crossed out because it's even. Did I just like miss a whole row of evens, guys? What's going on with me? I don't know how I missed all my even numbers. Miss Goldmark's just having a day, isn't she? Let's keep going. 41, 43, 47, 53, 59, 61, 67. Okay, this one. So here are our primes. I think it's kind of interesting to notice some patterns. One pattern that I find is really interesting is a lot of our primes, as we continue, I'm just going to use a pink highlighter to show, a lot of primes as they get bigger and bigger are kind of two apart, like 11 and 13, 17 and 19, 41, 43, 71, 73. So I find it interesting that oftentimes they're, you know, just 2 digits apart from each other. So this is a useful list to have. So it's nice to have your list of primes under 100 handy. Generally, knowing the smaller primes is probably the easier ones. So like 2, 3, 5, 7, 11, 13, 17, 19. Those are the ones that I remember the best. Like 23, 29, 31, 37. And then those are kind of like the next most useful. Generally, we use primes and try and figure out if any prime numbers fit into larger numbers. So generally, like, these numbers are the more common numbers that go into the numbers as we try and break them down. Generally, they're not so huge that we need some of the bigger ones like 97 or 83. So here are some divisibility rules that you probably learned back in school, and there are easy tricks oftentimes. So if it's even and ends in an even number, you know that 2 fits into it. 3 is if you add up the digits and the sum is divisible by 3, then so is the number. like the number 33, you do 3 plus 3, which is 6, and 3 can go into 6, so you would say check. It is divisible by 3. Number 4, divisibility, something I don't really remember learning about in school so much, which is if the numbers formed by the last 2 digits is divisible by 4, then the overall number. So it's like if you have 124, you would only have to check these two, the last 2 digits, and say, okay, well, 24 is divisible by 4, check. And I don't think I really learned that one in school. For divisibility by 5, it has to end in a 5 or a 0. That's pretty self-explanatory. 6, if you double check 2 and 3 and they both work, then you're good for 6. There's not really a good trick for 7, apparently. You just have to use regular division. 8 is kind of similar to 4, except for it's saying, like, if you have maybe like 5, 1, 2, 4. If you check, oops, I don't know why I put an extra 1 there. If you check the last 3 digits, and that's divisible by 8, then you would have confirmation. So I think it's kind of interesting, something that you guys might want to explore later when we do activity time tomorrow. I do have an activity where you're going to explore like why these rules work. It might be interesting for one group to like compare 4 and 8 and kind of build in why you need 2 rather than 3 digits. So that might be something cool if you're interested in that to explore further. If the sum of the digits is divisible by 9, similarly, like this kind of builds into the 3 idea, like if there's, you know, commonalities where those are coming from. And then 10 if the last digit is a 0. So we're going to do some more difficult divisibility problems. Okay, we're going to do that. We're going to learn a little bit about 11. The 11 stuff I might have to do in a separate video if I run out of my 15 minutes. So we'll see how we work on time. So let's look at some practice problems for divisibility. What is the smallest 4-digit number that's divisible by 2, 3, 4, 5, 6, 8, 9, and 10? And the hint is use reasoning or prime factorization. And prime factorization is just the idea that any number can be written as a multiplication or a product of primes. So like the number 26, I can break that up. I know that it's divisible by 2, right? And I would say, okay, how many 2s? 1, 2, and 1, 13. And that one's not so, useful. 26 is 2 times 13. But something like if you have 8, your prime factorization would be 2 times 2 times 2, which is 2 to the 3rd power. If you had maybe something like 20, that's 2 times 2 is 4. 4 times 5 is 20. So you'd write that as 2 squared times 5. Now this kind of goes nicely into why 1 is not prime. So the reason why is because there's this big theory within number theory that every number has a unique prime factorization. Key thing there is unique prime factorization. So every number has that. If 1 was a part of a prime factorization, I could say, oh, instead of that, I would make it 1 times 2 squared times 5. Or I could do like 1 to the 100th power times 2 squared times 5 would also get you 20. So because like multiplying something by 1 doesn't really change anything, we don't consider that prime because then we wouldn't have a unique prime factorization. So that's what I think of as to why 1 is not part of that. So let's go back to the problem. We've now talked a little bit about what a prime factorization is for context. If I want to be divisible by all those numbers, I need 1, 2, 1, 3, to have the 2 and the 3. The 4, that means I just have to have another 2, right? Because 2 times 2 is 4. To be divisible by 5, I need to add in a 5. So we're kind of building a prime factorization here. I'm already divisible by 6 because I have 1, 2, and 1, 3. To be 8, I need 3 2s, because remember we said the prime factorization of 8 was 2 times 2 times 2. To be divisible by 9, I need a 3 and another 3, right? 3 times 3 would give me 9. And 10, I already have a 2 and a 5, so I'm definitely good on 10. So multiplying that product all together, when I put everything together, I get 360, which is not a 4-digit number. So what I did was I doubled it, and then I doubled that, and I tried tripling it. And the smaller number was the 1080, so that would be your final answer.
The trick is just to keep multiplying by the smallest primes possible. So just trying a couple 2s or a 3 to see what the smallest 4-digit number is.